this is a demonstration of simple harmonic motion. We have a cart that is attached to a spring on either side, and it's mounted on a base, and if we displace the cart a given distance, we will be able to see it oscillate back and forth about its equilibrium position. So if we take a look at what simple harmonic motion looks like on a graph, we have our mass on a spring bobbing up and down, and that motion will be traced out by this pink curve here. The amplitude of the curve will be represented by A. The equation for this curve is just the position is equal to the maximum amplitude times the sine of omega t, which this represents the sinusoidal motion of this object. We can replace omega t with the square root of k over m times t, where k is the spring constant and m is the mass of the object. The period of this curve is represented as 2 pi times the square root of m over k, where again m is the mass and k is the spring constant. The frequency is just 1 over the period, so we can represent that with this equation here. If we go ahead and displace our cart, we'll be able to see this simple harmonic motion in action. So let's go ahead and do that. As you can see, I displaced it by a max value x equals a, and you saw that it bounced all the way through equilibrium to negative maximum x equals negative a, and back again. My question to you is, what happens if we change the mass of the cart? The cart here, say, has a mass m1. If I place 3 masses on top of that, this now becomes a mass of 4m. If we take a look at our equations here, the frequency is dependent on the mass of the object that is being acted upon. Therefore, if we increase the mass, this fraction will get smaller, therefore the total frequency should be less. Well, let's go ahead and observe that. I'm going to displace it by the same amplitude, and here we go. As you can see, the frequency was much slower than when it was with only a single m mass. Now let's go ahead and look at the energy of the system. So the total energy of the system is just the addition of the kinetic energy plus the potential energy. And we can represent the kinetic energy with 1/2 mv squared. And we can represent the potential energy as 1/2 kx squared, because all of that potential energy is stored within the springs of our system. If we go ahead and take a snapshot of the motion of our cart at 2 specific positions, one where the cart is traveling through its equilibrium point, and the other where it's traveling at the very end of its oscillation when the displacement is at a maximum, we can analyze the energy at each situation. To begin with, if we look at the equilibrium position, we know that the displacement of the object from its equilibrium will be 0, because it's there. And this forces the potential energy component of the energy equation to go to 0, because there is no stored energy within the spring of the system. Therefore, the energy can just be the kinetic energy, which is just 1/2 mv squared, where the velocity of the cart is maximum. At the other snapshot, if we look when the cart is at its maximum extension, where x equals a, the cart has gone through the equilibrium at max speed, has stretched out and stopped before it reverses direction. And that is where we're taking our snapshot. And because it is stationary, we know that the kinetic energy has gone to 0. Therefore, all of the energy in the system is in the form of potential energy, which is stored in the spring and represented by 1/2 kx squared. So my question to you is, We saw that mass has a direct relationship to the frequency of oscillation of our cart. So what's going to happen if I change the mass of the cart mid-oscillation? Well, we're going to look at it in two situations. One when we remove the mass at the equilibrium position, and one when we move the mass at the maximum extension position. So, we're going to be looking at this frequency equation here. If I extend this to its maximum position and let it go and remove the mass at this maximum position, we know that already mass has a direct relationship to the frequency. So if we decrease the mass, this fraction will get larger, therefore the frequency should increase. The other thing to look at is the energy of the system. So if we remove the mass when all of the energy is stored in the spring, there is no mass relationship to this energy value. Therefore, the amplitude of this oscillation should still remain out to the x equals a. Let's go ahead and observe that. 3, 2, 1. Three, two, one. As you can see, the frequency definitely increased and the amplitude stayed the same. My next question is what happens if we remove the mass as it travels through its equilibrium position? Well, looking back at the frequency equation, again we are going to remove mass, therefore that's going to get larger, therefore our frequency should increase. And since we're moving the same amount of mass, the frequency should actually increase to that same value. If we take a look at the energy of the system, if we remove mass at the equilibrium position, there is an energy factor that is related to the mass. Therefore, if we remove mass, the total kinetic energy will decrease. Therefore, it will never be able to reach this maximum amplitude again. Therefore, we should see an increase in the frequency, but a decrease in the maximum amplitude of the oscillation of this cart. Let's go ahead and confirm that. 3, 2, 1. Three, two, one. As you can see, the frequency increased to the same value as it did before, but the amplitude of oscillation of this cart was much smaller than when we removed the mass at its maximum extension.